Hello everyone, welcome to this video. In this video, let's answer this question and in regard to our study of properties of cosets, right? So the question here is, when can we say different cosets they are equal to each other, or can we say all the cosets they are equal to each other, or what is the condition under which two different cosets they are equal to each other? So the answer to this question lies in our property number 4 and property number 5. Let's have a look. Property number 4 tells us two different cosets which are generated by the element A and the second coset is generated by the element B. They are equal to each other if and only if we have A contained in the second coset BH, right? So this is if and only if part. So that means if A is contained in B of H, so AH is equal to BH. So this inverse also represents this thing, that a left coset of H, right, that is uniquely determined by any one of its elements. So B, we have some coset, right? This is B of H. It contains very many elements. If you select one of such element, let's call that element as A. So that means this A is a member of BH. In that case, this B of H is represented by the coset which is generated by this element, which is A of H. So this is what this properties tell you. In particular, if you take any element of a left coset, that can be used to generate the coset. Suppose now we take another element C from it, right? So then in this case also C belongs to BH. So in this case also C of H would be equal to B of H. So this B of H could be represented and would be equal to any of the coset which is generated by some element which is present within it, right? So this is the property here, and the proof of this property is also very simple. So let's have a look here. For the proof we have to prove if and only if part. So let's first of all take AH is equal to BH, and then we will prove that A is contained in BH, right? So let's assume AH is equal to BH. Now in this case we can write this A. Now we start with this A and we will reach at the set coset BH. So we can write this A as AE, and this AE is present in AH. Why? Because E is present in H. E is a member of H. So and this AH is equal to BH. So that means this A is now also present in BH. And this is what we wanted to prove in the first part of the result. For the second part, now we assume that A belongs to BH is there with us, and we wanted to prove that this AH is equal to BH, right? So for this, what we do here, we have A belongs to BH. Now if A belongs to BH, so this A could be written as some element B, small b of this, this small b is the same, right, multiplied with some element small h of this subgroup capital H, right? Okay, so therefore what would be A of H? In place of A, you can now write B of H, right? And by the property of associativity, by the property number 3 that you have studied here, right, the associative property, here you can shift the brackets. So using this property here, this BH of A would become B of H of H, right? And what is H of H? Now you know H is a member of capital H. So therefore H of H would be equal to H only, because this H absorbs all the elements which are member of that particular subgroup. So therefore this is equal to B of H. So from here we have this AH as equal to B of H, and this is what we wanted to prove here for this particular property. Moving forward on to our next property. So next property also tell us about different cosets, when these different cosets they are equal to each other. So let's have a look. Here it tell us that this AH would be equal to BH if and only if the element A inverse B would be present in the subgroup H. So this is the property. Now this property also shows that how we may transfer a question about equality of two cosets. We were initially talking about two cosets being equal, right? So now how we can shift this thing to something about H. which is a subgroup of G. So we are shifting this equality onto a question about H, so that it would contain this element or not, right? So this is what, and how this is what is good about this property, that it helps us in various proofs by linking this equality of two different cosets with that of the subgroup H, right? So this is about the property. Let's move forward onto its proof. For the proof here, we assume first of all that AH is equal to BH, and we would like to prove that this A inverse B is present in H. So from here, from the property, so let me just clean the area. So from the property here, AH is equal to BH, this thing would be there whenever we have A inverse B is equal to belongs to H, right? So if you look at this thing over here, AH is equal to BH. If we pre-multiply on both sides by A inverse, what do we have? A inverse B of H. So this thing becomes identity. So we have EH is equal to A inverse BH, and this thing further could be written as H is equal to A inverse B of H. So therefore this thing is there if and only if we have H is equal to A inverse B of H, right? And now we can use this property that we have already studied, that H absorbs one of its element when it is multiplied to itself, right? So A of H is equal to H if and only if A belongs to H. So in this case, this implies AH is equal to BH if and only if. Now here we are saying we are using this property here, A inverse B of H is equal to H. So that means this A inverse B has to be there in H. Then only it will absorb this A inverse B, na? So that is why this A inverse B of H is equal to H implies A inverse is equal to H. And this is the if and only if part. So we have proved both the things, because the result that we are using also uses this thing if and only if. So A of H is equal to B of H if and only if A inverse B belongs to H, and vice versa. So I hope you understood this answer here, these two properties, and the answer to this question, that when can we have different cosets and when can different cosets be equal, what are the conditions. So I'll see you in the next video.